In the previous video, we studied the formal properties of determinants and how to compute them by row reduction. And in this video, we'll continue studying determinants, and we'll look at minor expansion and the Kramer's rule, as well as discussing the interpretation of the determinant as a volume with the sign. So in order to compute the determinant of a matrix, we first row reduce it and then keep track of any row switches and rescaling of the rows. And in the end, we multiply all the contributions together. So the inverses of the row rescaling factors, the diagonal entries of the final echelon matrix, and the sign, which is -1 to the number of row swaps. So that will be the determinant of the original matrix. And it will be, to do this will be much faster than summing all the terms from the definition of the determinant, both if you do it on a paper or if you teach your computer to do it. So take this 4x4 matrix and do the row reduction, and by keeping track of rescalings and row switches. So first row, then we would multiply by -2 and -3 and add them to second and fourth row respectively. Then multiply the second row by -1, right? So to secure the pivot, sort of to have this pivot 1 over here, and then continue row reduction. So at this step, we're taking care of third and fourth rows. Then multiply by -1 and swap the rows 3 and 4, right? Right, and then the divide by multiply by -7 to get the matrix in the echelon form, right? So this is the upper triangular matrix, and as we discussed, where it's very easy to compute its determinant. So the determinant of this the matrix from the last iteration, just the product of all the ones, which is 1, and then we need to multiply by sort of by all the factors here. So here we had to divide by a factor by 7, which means that we need to multiply back by 7, and then multiply by -1 twice, which does not change the sign, so that the answer is equal to -7. Okay, so now you can try it by yourself. So first do the row reduction, and then apply the rule. So row reduce, keeping track of rescaling on row switches. So if you do this, you'll end up having this partial answer, which you still need to simplify a bit, and the final answer will be equal to 51. You can check yourself. Now, let's get back to the determinant. Recall that in 2x2 case, if you have a matrix A, B, C, D, then its determinant is equal to AD minus BC. And we had the rule of how to assign the minus signs to each of those contributions. In 3x3 case, we have 6 terms. 3 of them come with plus sign, three of them come with the minus sign. But instead, so let's talk about a different presentation, different perspective of how to compute this. So let us combine the first column here, right? So the 2 contributions that contain A in them. And then we do the same with 2 contributions that contain B and 2 contributions that contain C. So these 2 terms, AEI minus AFH, we can denote like this. It will be A multiplied by the determinant of the matrix EFHI. So here, there are no inversions in this sort of orange-green submatrices, right? So because they are ordered. Then the second group of terms which contain B, right? They have they have minus BDI plus BFG. And again, we can arrange them as B multiplied by the determinant of the matrix DFGI. And now there's a minus sign because there's one orange-green inversion. So you can draw an arrow from the bottom left to top right, like this. And there's one arrow, so hence there's one, there is a minus sign. Okay, and the final group of terms contains two inversions, or two orange-green inversions. So if you could have treated the column of green matrix as one unit, so this will give you CDH minus CEG, which you can combine as shown here. So this is called minor expansion. So for a matrix A, we can write A with I and J excluded, right, for the matrix formed by omitting row I and column J. So it will be a matrix of size 1 less, right? So if A was n by n matrix, this matrix with omitted row and column will be a 2 by 2 matrix. So if you have a 3 by 3 matrix as such, then its determinant is equal to, well, the combination of these three terms, as we saw on the previous slide, which we can write as A11 multiplied by A1 slash 1 slash minus A12 A1 slash 2 slash plus A13 A1 slash 3 slash. So we're slashing or removing those indices. So here we remove the first, row and first column, right? And we get the matrix A22, A23, A32, A33. Here we remove the first row and second column, and here we're removing the first row and the third column. And computing the determinant of the resulting of the remaining matrix, which has one less row and one less column. So more generally, by the same argument for a square n by n matrix with entry Aij in row I and column j, and then for any k from ranging from 1 to n, there is a minor expansion of the determinant along the kth row. And here's the formula. So it's the sum over j ranging from 1 to n, and then there is a minus 1 to the power of j plus k. So this takes into account all the inversions that we have, multiplied by akj, and by the corresponding minor. So these are called these determinants with the removed row determinants of the matrices with the removed rows and columns are called minors. And a minor expansion, you can analogously consider the expansion along the kth column. So here it's ajk instead of akj. So we're fixing the kth column and then ranging and then the sum goes over the first index, which sort of shows you the entries along the column. The sign convention, so here this is the sign contribution from the previous formula. So we have minus 1 to the power j plus k, right? And those are indices which enumerate rows and columns. And then you can see here that because of parity, this is the pattern of the signs, right? Which accompany the corresponding terms in the expression for the determinant, right? So which means that if you have A11 times the minor times this minor, it goes with the plus sign. Here A12 goes with the minus sign, A13 with the plus sign, and so on and so forth. So let's compute this determinant of this matrix by expanding it along the second row. And so we're taking the second row because it has 1 0 in it, right? So that will help us to simplify the computation a little bit. You could have also taken the third row, which also has a 0 in it. Yep. So that's what this procedure does, right? So we take, so first it's a 2 multiplied by minus sign because of the inversions, right? So see the previous slide for sign convention, multiplied by the determinant of the matrix where we remove the first column and the second row, and so on. So then plus 0 multiplied by second row, second column, but it's relevant because it's multiplied by 0, and 2 more terms according to this formula. So that's what you get. Now we reduce the problem of computing the determinant of a 4x4 matrix to computing the 3 determinants of the 3x3 matrices, right? If you exclude the one with the 0 here. Well, you know, it's a painful exercise, but we can now do the so as an exercise, let's do the again the row reduction, second row reduction for each. So this one doesn't have any zeros, but these others they do, right? So here's what the formula, here's what the calculation will tell you. So the first determinant is equal to 5, the second determinant is equal to -1, and the last one is equal to 0, luckily for us. I'll pause if you need to, if you want to check this computation by yourself. So let's now compile everything together. So that's what we ended up after the row reduction of the 4x4 matrix. So if you plug in those answers, and see here, there's a question mark. So we did not attempt to calculate the determinant of this matrix because it's irrelevant, right? Whatever it is, it multiplies 0. So there will be no contribution. So the answer is equal to -7. And if you compare it with the previous calculation, you see that it's the same answer. Now, you tell me which one is easier. Okay, now compute this. Let's compute this determinant of this matrix by row reduction. Try it and see if you get the right answer. Now let's talk about the formula for the inverse of a matrix. Consider matrix A, 3x3, like this. So determine the adjoint of A to be filled with this these minors, right? So its matrix elements will be minors, the corresponding minors, together with the signs that come from the convention of computing the determinant. So here we have plus A1/1/, here it's minus A2/1/, and so on. So pluses and minuses, they alternate in the chessboard pattern here. Now let's multiply A by adjoint A in this order, right? So if you do it diligently, that's what you're going to get. Each entry will have 3 terms, right? Because that's how matrices are multiplied by each other. Now, if you look at the diagonal terms, for example, the first one, it will look like this. So these are minor expansions of the determinant of A, right? So it's the exercise, this story that we just talked about, right? So now let's look at off-diagonal entries. Say the 2-1 component. So A21, so we have this A21, A1/1/, minus A22, A1/2/, plus A23, big A1/3/. So, well, we can now use the definition of those minors. We're going to get this. So this quantity over here, what is it equal to? So it turns out to be the minor expansion of this determinant, right? If we have A21, A22, A23, A21, A22, A23. So what is it equal to? It is equal to 0 because the first 2 rows are identical, right? So determinant of the repeated matrix, determinant of a matrix with repetitive rows vanishes. And the same is true for all other off-diagonal term, as you can check by yourself. So therefore, if you take these two matrices and multiply them one by another, we'll get a scalar, which is equal to the determinant of A multiplied by the identity matrix. And moreover, you can repeat this exercise in a different order. So you multiply adjoint A by A in this order, and in that order, the answer will be the same. So this holds for any square matrix where this adjoint A ij, so the ij's component of this matrix is equal to -1 to the power I plus j times the minor AJI. So see, there's a swap of indices here. So the ij's component of this adjoint matrix is the AJI's minor, as you can see from here. So the entry in row I and column J is adjoint A. So it's determinant of the matrix, which is formed by removing column I and row J of the original matrix A itself, multiplied by the sign factor. So keep in mind this last comment; it's very important. Okay, so let's sort of see how this works for the 2x2 matrix, right? So this will be the adjoint matrix for it. So it will look like, so what happened is that we swapped around the diagonal elements D and A, and then the off diagonal elements, they just exchange signs. Because when you calculate the minor, right? So the minor for B, so the minor for element 1, 2 will be, you need to remove this row, this column, and this row, and multiply by the minus sign, which is B itself. And the same happens with C. And a quick verification shows you that it works, that the calculation is correct. Now let's talk about Kramer's rule. Consider matrix equation AX equals B, where A is a square matrix. Then determinant A multiplied by X is we can present it as, so there's like identity matrix multiplied by X, and identity matrix is adjoint A times A, right? Times the determinant times X, so that's adjoint A times B. Now it takes the ith row of the column vector on both sides. So we'll get this formula. So determinant A times xi is equal to sum over j minus 1 to the I plus j, the AJI's minor times bj, the j's component of the B vector. That is the minor expansion along the ith column of the determinant of the matrix formed by replacing the ith column of A by B. So this allows us to construct the solution of the inhomogeneous system of equations like this, right? So that's the kind of the formula for the answer for the ith component of the vector here. So let's take a square matrix, assuming the determinant. Yeah. So by the way, determinants are defined, at least the way that we define them, for square matrices, right? So if it's non-zero, then we can divide by it, right? So xi will be the determinant of a matrix where we place the column I of A by vector B, scaled by this determinant. Okay, so now just some pieces of advice. Never use these formulas in real life, like when we do the computation. So as we saw, taking the determinant of a 4x4 matrix by minor expansion was more difficult than the row reduction. So it only gets worse as the size of matrix grows higher and higher. And likewise, the row reduction beats computing this adjoint for inverted matrices, and it beats Kramer's rule for solving systems. So those formulae that we just talked about, the Kramer's rule and the computing adjoint, they are good for proving various theorems in linear algebra. but they're not very effective and they're very efficient in practical applications. So why to learn it? Yeah, so one reason I just said, and the other one is that sort of it's conceptually satisfying to know that not only there's a procedure for solving these equations, but also there's a closed formula. And yes, you can use this closed formula to study properties of the solutions. Now, interesting fact about integer inverses and those solutions. So say you have an invertible matrix with integer entries. You can ask yourself, well, does the inverse also have integer entries or not? Well, now you know when. It only happens when the determinant of this matrix is either +1 or -1. Because if it's not, then you divide by something different from 1 and -1, and that will give you fractions, at least in some places. Right. Now, observe that the determinant of m times determinant of m inverse is determinant of m inverse, which is 1. So the determinant of an integer matrix is always an integer because it's made by additions and multiplications. If m inverse has integer value, integer entries, then determinant of m and determinant of m inverse are two integers which multiply to 1. So both must be either +1 or both are -1. Right, so yeah. So determinant of m is 1, determinant of m inverse is -1 is 1, or both are equal to -1. And similarly, the adjoint of the matrix is also an integer because it's made by additions and multiplications. So if the determinant of m is equal to +(-1), then m inverse is the adjoint of m divided by the determinant of m is an integer matrix as well. And similarly, if you talk about solutions of inhomogeneous system of equations, so assuming that a is square and has integer entries, b has integer entries, determinant of a is equal to +and -1. We just saw that the E inverse has integer entries, and therefore the unique solution, right? It's unique because the determinant is non-zero, so A has all columns are pivot columns. The solution X is equal to A inverse times B also has integer entries. Okay, and the last story for this video are volumes. So we have an intuitive notion of what volume means, right? It's the amount of space that occupies by a body, like, it's a pail of water, right? A mug of coffee mug or something like that. So let's talk about cubes of fixed side and length for simplicity. So, and we think of volume of the solid S as the number of cubes that fit inside it. Right, sort of this kind of standard calculus-like approach, and then if you like, you can send the number of those cubes to infinity by making their size smaller and smaller, like this, right? So you would create a mesh, right, with the size epsilon, right, and then you would multiply this number of cubes of side epsilon that fits inside S by epsilon to the sort of divided by epsilon to the power of the dimension of this of space. So in 3 dimensions, it will be epsilon to the -3rd, but you can do it in any dimension, including higher dimensions, say hypercube in 5 dimensions. It works equally well there as well. You can even consider fractional dimensions. So that's something that you want to. In some physics applications, it plays a role. Okay, so that's the volume. Yeah, so, and we'll only count the cubes that fit completely inside. So consider linear transformation T from Rn to Rn, and given a set X, we want to think about how the volumes of X and T of X would compare. The key observation is that the number of cubes inside X is the same as the number of T transformed such cubes in T of X. Right, so the cubes, they don't go anywhere. So there's a picture on the left in red, and then sort of here we apply a shear transformation, but it contains the same number of squares or parallelograms in this situation. So the number doesn't go anywhere. What may change is the volume of each cube. So now, observing that the failure of these to pack correctly at the boundary is washed out as epsilon ascends to infinity, so we can conclude that sort of in this continuous approximation, the volume of x divided by the volume of each cube is equal to the volume of the image of t of x divided by the volume of the image of each cube. Or if you want to rearrange this, you can say that the volume of t of x is the volume of t of cube, right? So there's like it's a coefficient which sort of rescales the volume of a single cube times the volume of x. So finally, we need to understand what's this coefficient is equal to. So in other words, by how much is the volume of a single cube is rescaled under this linear transformation, right? And then it's, as you can see from this consideration, this will be a universal result which applies to any shape. So let's take two linear transformations T and S from Rn to Rn, and we apply the formula from the previous slide to the set S of cube. So if x is equal to S of cube, we get this formula. So here we have a composition T of S of a elementary cube is equal to this thing. So equivalently, the function v, which is the function from the space of linear transformations into R that takes T or its matrix into volume of image of T, image of a unit cube under T. So this so it's a rather complicated linear functional, right? It's an infinite dimensional space. There are infinitely many linear transformations. It respects multiplication in the following sense, right? So that v of t composition with S is equal to v of t multiplied by v of S. Take a moment to kind of digest this part. And note that since v of the identity is equal to 1, so this if you take an identity transformation, then its image under this map is 1, and then if it's a non-invertible transformation, that the volume is equal to 0. So now we consider any linear transformation. So if it's not invertible, then v of t is equal to 0. If it is invertible, then you can use row reduction and expand it as a product of elementary matrices in this order, En through E1. And now, since volume scaling is multiplicative, we get V of t is equal to V of En and so on, V of E1. It finally remains to understand the volume scaling of elementary matrices, of elementary operations. So scaling of row means stretching a coordinate rescales the volume by the same factor, right? So the volume of a box is the product of its side lengths, right? So in 3 dimensions, it will be, x times y times z, and rescale one of them. Then switching the rows doesn't change the volume at all, right? So you're just renaming which directions is x, which directions is y, which is z, and so on. Then adding a multiple of one of the row to another takes a box to a parallelepiped, as a typo, parallelepiped with the same base and the same height. So again, does not change the volume. So for an elementary linear transformation, the volume of the image of a unit cube under this linear transformation T is equal to the absolute value of the determinant of T. Volume scaling is multiplicative, of course. So this holds for any linear transformation. So it's a very sort of general universal result. So let's put everything back together because there was quite a bit of stuff that we did. So for any linear transformation T from Rn to Rn and any subset X in Rn, the volume of image of X under T is equal to volume of X multiplied by the absolute value of the determinant of this linear transformation.